All right, next up we have f of x equals the square root of x. The name for that, conveniently, is the square root function. Sometimes you'll see it referred to as a radical function. That's because that symbol, that check mark looking thing, is not a square root symbol, it's a radical symbol. It's only a square root if there's no number written there, or if it's a 2 written there. But if it's a 3 written there, then it's a cube root, or a 4, a fourth root. Now, making a quick table out of this, thinking about what we know about square roots, we can't plug in negative numbers and get real output. So let's start with 0. The square root of 0 is 0. The square root of 1 is 1. Now I'm going to skip the square root of 2 because it's not a nice square number. The square root of 2 is the square root of 2, and that's hard to graph. So let's graph the square root of 4. So that'll be 4, 2, and then let's do one more, 9, 3. So plotting these points, we got 0, 0, 1, 1, 4, 2, and then 9, 3 is going to be, let's see, 7, 8, 9 would be around here. So we're going to take those 4 points there, and we're going to graph them. And it's going to look something like that. The domain we're going to be working with is our x's. Those are real numbers, as long as our x's are greater than or equal to 0. We're not going to be plugging in negative values into the square root. The range that we're going to get, also dealing with real numbers for the y's, and it's also going to be y greater than or equal to 0. We're not going to get a negative output when we take a square root. The intercept, you can have one y-intercept, and you can also have one x-intercept. Now, things can get shifted around a little bit, so sometimes you could have 0 or just one of each, one of one, but not of the other. The one unique property of this one, it terminates on one side. What I mean by that is it ends. Like looking at the left side of this graph, it ends right at 0, 0. There's nothing going to the left of that. On the right side, it goes on forever and ever and ever. The next one in the upper right, 1 over x is a rational function. So we're dividing, we're making it into a ratio. Let's make it a quick table out of this. Now this one can be kind of hard to make convenient numbers, so I'm going to still do the -2, -1, 0, 1, and 2. We're going to take each of those x values and do 1 divided by that x value. 1 divided by -2 is -1/2. 1 divided by -1 is -1. 1 divided by 0 is undefined. 1 divided by 1, so 1 divided by 0, remember you can't divide anything by 0 and get a real output. So 1 divided by 0, well, how many times does 0 go into 1? Well, you keep adding 0 over and over and over and over, and it still doesn't get you to 1. So that's why we're leaving it as undefined. 1 divided by 1 is 1. So we have 1, and then 1 divided by 2 is 1/2. So these coordinates, I'm actually going to graph a couple more. So we have -2, -1/2, -1, -1. And then if we were to do like -1/2, we'd be down at -2. And this part of the curve looks like this. And goes down. Ooh, I missed a little bit. Goes down forever that way. On the other side, we had 0 is undefined. We're not going to apply anything at 0. We had 1, 1, 2, 1/2, but we'd also have 1/2, 2. This one has got this similar shape. And both of these curves are going to get really, really close to the x-axis and really, really close to the y-axis, but never quite touch it. As a result, for our domain, we're going to say our x's are real numbers still. However, x cannot be equal to 0. We cannot divide by 0 and get a real or get any output. It's undefined. Our range is going to be y are real numbers as well. But also, in this case, y cannot be equal to 0. There's no way in order to do 1 divided by a number and get 0 as an output. Now, the intercepts, there are none. But there can be some with transformations. We'll talk about transformations I think it's in 1.7. So there can be some with transformations. So we'll talk about what that would look like later. But this one has no x and y intercepts. Let me shift me over here so we can, there we go. Other properties, big word here, asymptotes. Those lines that it gets really, really close to but never quite touch, those are called asymptotes. So if you were to draw a line on the line x equals 0 or y equals 1, aka the x, sorry, my goodness, I can't speak right now. X equals 0 and y equals 0, the x and y axes, those are asymptotes. It gets really, really close to it but never quite touches it. Oh, sorry. Down at the bottom left, let me shift my image again. Cool. Down at the bottom left, we have f of x equals the absolute value of x. We give the creative name of an absolute value function. Now remember, absolute value means the distance away from 0. So it's not always, like I know some people say, well, if it's negative, make it positive. If it's positive, keep it positive. That's just clunky, because what if it's 0? 0 is neither positive nor negative. So it's the distance away from 0. So like -2 is 2 spaces away from 0. -1 is 1 space. 0 is 0 spaces away from 0. 1 is 1 space. 2 is 2 spaces. So if we plot these points, it's going to form the good old flying V shape. For our domain, you can plug in whatever x value you want, get an absolute value of it. So we're going to say our domain x is an element of the reals, call that good. Our range, y's are real numbers, but if we're doing just the parent y or parent absolute value function, you're never going to get a negative output. So we're going to say our y values are greater than or equal to 0. Our y-intercept, there's always going to be one y-intercept. In this case, you can see it's at y equals 0 at the origin. And you can have up to 2 x-intercepts. You could have 0 depending on where it's shifted, or you can have 2 if it's shifted down below, or like this graph, you can have just exactly 1. The symmetry, and I'm going to refer back to that axis of symmetry, it's reflective over the y-axis or your axis of symmetry. I'm going to abbreviate it AOS. No other unique properties we need to talk about for this one, so we're going to move on to the last one. The last one, it's kind of clunky, and I'm actually going to use a slightly different notation. So I'm going to zoom in and let me move my image so that it's not in the way again. We're going to zoom in, and this one, I'm actually going to change the notation to, it looks like half of a bottom bracket or a lowercase l, or half of a square bracket, sorry, or a lowercase l, and then kind of the other half of a square bracket or backwards lowercase l. This one is a specific type of function. We're going to call it a step function, or like one of the fancy names for it is the greatest integer function, which I think is a confusing name. So the name that you will often hear instead is referred to as a floor function. What this means is you're going to take whatever decimal it gives you and round down to the next integer, unless it's already on an integer. So the reason it's called greatest integer, like the formal definition is, it's the greatest integer less than or equal to the current or the number that you're given. It's clunky. Let me test out a couple numbers and show you what I mean. So since this is going to involve some rounding, we're actually have to choose some decimals. So for example, if I do x equals 3.5, the floor function, we would round it down to 3. 3.9, we would round it down to 3. So you're always rounding down, even though you're like, if you were to do traditional rounding, you'd be rounding it up in those cases. You're going to be rounding it down to 3. So like, even if I get to 3.999, etc., well, I'll just do 3 decimal places, it would still round down to 3. Once we hit 4, well, to round to the nearest integer, it's just 4. Then if I were to do 4.0001, it would still round to 4. 4.999, it would round down to 4. But then we hit 5, it would round up to 5. So taking a look at some of these values that I have here. So let's see, 3.5 was the first one I chose. 3.5 would round down to 3. 3.9 would round down to 3. 3.99999. But then once we hit 4, it jumps up. So in other words, let me zoom in on this a little bit. In other words, this part of the graph right here gets so close to being at 4.3, but once it hits that, it gets really close to that dot, but then it hits that and jumps up. Then we had a dot at 4.1 and 4.999, and it's going to hit everything in between here. But once we hit 5, it's going to get really close to that dot there, but it's going to jump up. And this pattern is going to keep on going. Now you can kind of see why it's sometimes called a step function, because it forms some steps. Now for time's sake, I'm not going to graph every single point on here, but you can kind of see how this pattern keeps going. And it forms a bunch of steps. Now the domain, this is where domain and range are going to get particularly specific. Domain, you can plug in whatever real x value you want. The range, you'll notice we're not going to hit every real value because we're only hitting like numbers without decimals. There's a name for the numbers without decimals. We could be positive, we could be negative. The y values are always going to be these things called integers. And here's the fancy notation. It's a z with like a little extra bar. Let me do a little bit better. So it's like kind of like the real numbers symbol. Let me zoom in a little bit. But instead of like an R with an extra bar on it, it's a Z with an extra bar on it. And again, this specifies that it is just a bunch of integers. So this one, again, the y values are going to go, you're never going to get a y value of 1.2. If you're at an x value of 1.2, you're going to round down to 1. If you're at 1.999, you're going to round down to 1. You're never going to round to another decimal. It's kind of goofy.